We're back with the impossible question. Now this is part 3. Just to give you a context about what happened in part 1 and part 2, we looked at what this question is asking, which is how many ways is it possible for every row, column, and the long diagonals to be 9-digit multiples of 9, with the condition that whatever number we start with in the first column, we go in ascending order until we get to 9, and then we go back down to 1 and continue in ascending order. In part 2, we looked at some examples to try and build our intuition around how we could go about solving this problem, because it would take 12 years to check every single possibility individually. So we're not going to be able to do that to solve this question, but we're still going to need to check some of the possibilities to find a simpler way of doing this, to try and find some kind of insight or idea that's going to make it what looks like an extremely complex question a bit simpler to solve. So what we did notice was that every row, because it contains the digits between 1 and 9, is going to have a sum of 45. And we know that for any multiple of 9, if the digit sum is a multiple of 9, then the number itself is a multiple of 9. So digit sum 45, that is a multiple of 9, 9 times 5. So we're happy with every row. That's already made the question way easier, because now we just need to check the columns and the diagonals to check if it is a gorgeous grid. Now, we don't want to check all of them individually. So when we go across each column in a single row, we're adding 1 each time until we get to 9, and then we go back down to 1. Because if we just ignore the 9 for a moment, because we're just adding 1, everything in this second column is adding 1 to whatever is in the first column. Overall, we're just adding 9 total to what's in the first column. Of course, the other case is, well, what if we started with a 9? Well, then we're kind of adding 1 to get 10, but it's not 10, it's 1. We're subtracting 9 afterwards. So we're still added 9, but then we subtracted 9 afterwards. Now, if we are adding and subtracting 9 or multiples of 9 to something that is already a multiple of 9, then it's still going to stay a multiple of 9. What this is telling us is if the first column is a multiple of 9, then the second column is a multiple of 9. If the second column is a multiple of 9, then the third one is. And of course it cascades all the way down the columns. So the only thing we need to check is the first column a multiple of 9. If it is, we're happy, and all the columns are multiples of 9. That's a massive step towards solving this problem. But of course, we're probably wondering now, what about the diagonals? Isn't that going to be the most tricky part? We want to consider, is there a way we can connect the diagonals also to the first column? Because if we can, only thing we need to check is indeed this first column. And can we use some similar logic? This cell, 3, 3 in the grid, we're adding 2 to the number in the first column in the same row. And we keep going down the diagonal, then we're adding 3, adding 4, 5, 6, 7, and 8. Now, if we find the sum of the numbers, of course, in the top left one, we're adding 0. If we find the sum of the numbers between 0 and 8, it is 36, which again is a multiple of 9. Well, the only thing that we actually need to check is if the first column is a multiple of 9, then the diagonals will also be a multiple of 9, the columns will be multiples of 9, and we have a gorgeous grid. So what this question really just simplifies down to, we can just make it a multiple of 9. So for example, if the first 8 digits sum to 37, then we can just make the last digit an 8 so that they sum to 45, and it is a multiple of 9. That's always going to work. We have free choice of the first 8 digits, and the last one is fully determined. We have 9 options for each of these digits, 8 different digits. So we do 9 to the power of 8. The last one's determined, so it's almost like times it by 1. And this is how many 9-digit multiples of 9 there are, which is also the answer to our original question of how many gorgeous grids it is possible where we have multiples of 9 on every row, column, and long diagonal. If you like this 3-part series, drop me a follow and let me know which question you'd like me to solve next.